nanowire transistor is one of the candidates which has the potential to overcome the problem posed by the show channel effect in SOI MOSFET. In addition to this, it has improved gate strength, more electrostatic control on channel, excellent current drive, and have the merit that they are compatible with the CMOS processor. Some of the fundamental problem of MOSFET inspired device for less than 10 nanometer channel length expected to be electrostatic limit, source to drain tunneling, carrier mobility, process variation, and static leakage. It is demonstrated that by using Bohm quantum potential to include the confinement effect and by calibrating the BQP model against the 2D Schrödinger Gaussian equation, the scaling behavior of silicon nanowire FETs can be successfully predicted. My dear friends, there are two quantum models in Atlas TCAD. First one is a self-consistent coupled Schrödinger Gaussian model, and the second one is Bohm quantum potential model. We can obtain close agreement between these two models, BQP model and the Schrödinger Gaussian calculation equation for any given class of device. In this presentation, I will talk about Bohm quantum potential model in detail. This is the best model for nanowire FET in Atlas TCAD tool. Bohm quantum potential model. This model was developed for Silvaco by the University of Pisa and has been implemented into Atlas with the collaboration of the University of Pisa. There are two advantages of using Bohm quantum potential model over the density gradient method, or we can say that Schrödinger Gaussian equation. One of the advantages is it has better convergence property in any situation. And second advantage is you can calibrate it against results from Schrödinger Gaussian equation under condition of negligible current flow. My dear friend, the Bohm quantum potential model introduces a position dependent quantum potential Q, which is added to the potential energy of a given carrier type. This quantum potential is derived using the Bohm and represented it as shown in the equation Q is equal to this one, in which gamma and alpha are two adjustment parameter, and this one is the inverse effective mass. To use the BQP model for electron or holes, we need to specify BQP.N or BQP.P, BQP.N for electrons and BQP.P for holes in the model statement. We can also set the parameter value alpha and gamma and the direction of the quantization, or we can say that confinement. It is important. Next is calibration of BQP model. The first step of the calibration is to choose a suitable biasing for the device. The second part of the calibration is to set the appropriate BQP parameter in the material or model statement and to set the carrier 0 in the method statement. This will cause the BQP equation to be coupled with the Gaussian equation using the charge density term. N is equal to NC exponential minus EC plus QP by KT. Same for the P. So we can say that for holes. These are the default parameter for the gamma and the alpha. BQP.N gamma real value is 1.2. BQP.N alpha real value is 0.5. BQP.P gamma real value is 1. BQP.P alpha real value is 0.5. BQP.N gamma and BQP.P gamma parameters allow you to set the gamma parameter of the BQP model for the electron and holes respectively. BQP.N alpha and BQP.P alpha, these parameters allow you to set the alpha parameter of the BQP model for electron and hole respectively. You can specify BQP.N and BQP.P separately. But if quantum effects for electron and hole occur in the same device, then you can specify them together in the same model statement. Next one, BQP.QDIR parameter specify the principal quantization or confinement direction. BQP.QDIR1 is equal to 1 means for X direction, 2 for Y, 3 for Z, and 4 for radial direction. Or we can say that for 3D cylindrical structure only. For example, if a MOSFET channel is in XY direction, the direction of the confinement is in Z direction, you would set BQP.QDIR is equal to 3. For semiconductor with spherical band, BQP.QDIR will have no effect. The special case of BQP.QDIR is equal to 4 applies to 3D cylindrical structure only. It specifies quantization in the radial direction. Next is the numerical method used in nanowire. First one is Newton, second one is Bloch, and third one is Gumel. Newton. Specify the Newton's method will be used as a solution method in subsequent solve statement unless specified otherwise. Certain models and boundary conditions setting require that the Newton's method is used. If no solution method are specified, Newton is applied by default. Second one is Bloch. Bloch specify that Bloch-Newton solution method will be used as a possible solution method in subsequent solve statement until otherwise specified. The Bloch statement only has the meaning when either lattice heating or energy balance is included in the simulation. For isothermal drift diffusion simulations, Bloch is required to Newton. Third one is Gumel. Gumel specify the Gumel method will be used as a solution method in the subsequent solve statement until otherwise specified. If other methods, Bloch or Newton, are specified in the same method statement, each solution method will be applied in sequence until convergence is obtained. The order that the solution method will be applied is Gumel, then Bloch, then Newton. Next is the setting the number of carriers in the method statement. Atlas can solve both electron and hole continuity equation or only one or none. You can make this choice by using the carrier parameter. For example, method carrier 2 specify a solution for both carrier is required, electron as well as holes. This is the default. With one carrier, the electron or hole parameter is needed. For example, for hole solutions only, method carrier 1 hole. You can use method carrier 1 electron as well. To select a solution for potential, only specify method carrier 0. Next is setting the trap parameter in the method statement. Although Atlas provides several methods to overcome a poor initial guess and other convergence problems, it is important to understand the role of initial guess in obtaining each solution. The simplest and most effective method to overcome poor convergence is by using method trap. This is enabled by default. Its effect is to reduce the by-step if convergence problems are detected. Considering the example for the previous section, solve initial, solve V drain 2.0 volt. If the second solve statement does not converge, trap automatically cuts the barrier step in half and tries to obtain a solution for Vd is equal to 1 volt. If the solution does not converge, the by-step will be halved again to solve for VDS, the drain voltage is equal to 0.5 volt. This procedure is repeated up to a maximum number of tries set by the method parameter in the max trap statement. Once convergence is obtained, the by-steps are increased again to solve up to 2.0 volt. The default of maximum trap is 4 and it is not recommended to increase it because it can increase the simulation time. Since changing the syntax to use smaller by step 3, 2 or 1 is generally much faster is increase the speed of the simulation. The next step is setting the IT limit parameter in the method statement. Numerical method solutions are obtained iteratively. You change the maximum number of iterations permitted using the IT limit parameter on the method statement. IT limit controls how many iterations can occur for the BQP equation in solve initial. This is by default 10 into IT limit. For carrier zero solutions, the maximum number of iterations for the individual equation solved is DUMITS. The maximum number of outer iteration is set by IT limit. Method Newton block IT limit is set to 20. By default, the value of the IT limit is 25 and the value of GUMITS commits is 100. The maximum number of iterations for the individual equation is GUMITS commit. The maximum number of outer iteration is IT limit is set by IT limit. Next is setting the n block parameter in the method statement. After obtaining the parameters for BQP, either the drift diffusion or energy balance equation can be solved as usual. For cases when lattice heating is important, then LAT.temp can be enabled at the same time is used in the method statement. N block IT specify the maximum number of block iterations which control the number of outer cycle in the drift diffusion and energy balance cases. The maximum number of drift diffusion solution and the carrier energy solution iteration is set by the IT limit, and the maximum number of BQP solution is set by the GUMITS commit. The convergence may become unsteady when the carrier density is very high and Fermi statics is used. In this case, you may decrease BQP.nmix or BQP.pmix parameter of both to a value between 0 and 1. This will cause relaxation of Fermi factors between two consecutive iterations and result in steadier convergence. In the proposed nanowire FET structure, I am using the n block limit is equal to 30. By default, the value of the n block height is 50. Next is setting the VSAT mod.inc in the method statement. It specifies that the derivatives of the negative differential mobility will not be included into the Jacobian until the norms of Newton update for potential is less than the value specified by VSATD mod.inc. Modal field mobility and the value of this parameter is equal to 1. This is very useful since the negative differential mobility model is highly nonlinear and cause numerical stability problem. In my proposed structure in my program, I have set this parameter is equal to 0.01. Next is the BQP model for the insulator. The bomb quantum potential is automatically calculated in insulators. If you specify the semiconductor parameter in the material statement for the insulator, the drift diffusion equation will be solved in the insulator and will include the BQP correction. It is also recommended to set the density of state of the insulator to be the same as the semiconductor to which they interface. For example, silicon SiO2 interface system set material region N NC is equal NC at 300 Kelvin is equal to 2.8 10 raised to power 19 and the value of NV is equal to 1.04 for 10 raised to power 19, in which N is the region number of SiO2. The material statement set the conduction band and the valence band density of state at 300 Kelvin for N region. You can also set the BQP parameters on a material by material basis, which may be necessary for heterojunction based device. The BQP model is applied globally and cannot set on a region by region basis. This material statement for the region, for example, for region 2, this is the region for the SiO2, will set the conduction band and the valence band density of state at 300 Kelvin for this particular region, that is 2, for example. Combining the iteration method, you can start with the Gomel scheme, then switch to the block or neutron if convergence has not occurred within a certain number of iterations. One circumstance where this can be very useful is that Gomel iteration can define the initial guess to a point from which neutron iteration can converge. The number of initial Gomel iteration is limited by GUM.INI. You may want to use block iteration and then switch to the neutron if there is no convergence. This is the recommended strategy for the calculation that included lattice heating or energy balance. The number of initial block iteration is limited by setting the value of n block IT in the method statement. Any combination of the parameter Gumel, block and neutron can be specified in the method statement. Atlas will start with the Gumel method if it is specified. If convergence is not achieved within the specified number of iteration, it will then switch to the block if block is specified. If convergence is still not achieved, the program will then switch to Newton. Next is the specifying 3D structure. The syntax for forming 3D device structure is an extension of the 2D syntax described in the previous videos. The mesh statement should appear as mesh 3.d or 3.d. You can use either a mathematical value or you can use alphabetical value. The 3.d parameter tells Atlas that a three-dimensional grid will be specified. The other statements used to specify 3D structure and grids are the same as for the 2D with the addition of Z direction specification. For example, we are using the X meshing, location 0, spacing 0.15, location 3 and the 0.15. The X and Y location and meshing is the same as it is in the 2D structure code, but in this the Z meshing is added to show the device in the 3D form. This meshing defines a 3D mesh that is uniform in the X and Z direction and varies in the Y direction because spacing is same in X and Z direction. Position parameters for the Z direction are Z minimum and Z maximum are also used on reason, electrode and doping statement also. Using the command language to define a structure, you can model a quasi 3D structure in Atlas 2D by specifying the cylindrical parameter on the mesh statement. There is one drawback of this structure has no independence on the angle around the axis of rotation. Specifying quasi 3D cylindrical structure. In Atlas 3D, the cylindrical parameter enable you to create a general cylindrical structure. The mesh statement must appear mesh 3D cylindrical, where the 3D parameters inform the simulator to create a fully 3D mesh. When specifying the cylindrical, you must now specify the structure in terms of radius, angle, and Cartesian Z coordinate. There are three mesh statements analogous to those used for the general structure that are used to specify mesh in radius, angle, and Z direction. The three meshing statements are used. The r.mesh statement is used to specify radial mesh. The e.mesh statement is used to specify angular mesh, and the z.mesh statement is used to specify mesh in the z direction. For example, mesh 3 dot structure, this code is given in the presentation. R.mesh from 0 to 14 nanometer, angular mesh, and the z.mesh. Here the r.mesh lines are similar to the familiar x.mesh, y.mesh, and z.mesh, except that r.mesh location and spacing are radial relative the z-axis in micron. The location and spacing on the angular mesh line specify degree of rotation about the z-axis. The z dot mesh lines are exactly the same as have already been discussed in the last slide. For 3D cylindrical structure, specifying the region electrode statement also are modified to allow specification of ranges in terms of radius, angle and z location. The range parameters are R minimum, R maximum, A minimum, A maximum and Z minimum, Z maximum. R minimum, R maximum, Z minimum and Z maximum all are units of micron, but A dot minimum and A dot maximum are in degrees. Next is the unit of current in log file in case of nanowire FET. Generally, the unit of current are written in the log file. In Tony plot, it is ampere per micron. This is because Atlas is a 2D dimensional simulator. It sets the third dimension or z direction to be 1 micron. Thus, if you compare the Atlas 2D simulation result for a MOSFET versus the measured data from a MOSFET of width 20 micron, you need to multiply the current in log file by 20. There are 4 exceptions that we will discuss two in this slide. In the 3D modules of the Atlas, the width is defined in the 3D structure. Therefore, the unit of the current are ampere in case of 3D structure. And the second is when cylindrical coordinates are used, the current written to the log file is integrated through the cylinder and is also in ampere. Similar rules apply for the capacitance and the conductance produced by the AC simulation. These are usually in 1 ohm dot micron, or we can say that mho per micron and Faraday per micron respectively. For capacitance it is mho per micron and for conductance it is Faradays per micron. For more understanding how to use these parameters in the Silvaco Atlas, let's go to the code in which I will explain everything how you can implement nanowire FET in the Silvaco Atlas TCAD tool. My dear friends, this is my code. You can note down this code step by step and simulate the same code in your Silvaco TCAD Atlas. You will get the same result as I got. Let's start with the code. First statement is go Atlas. Second is the meshing 3.d cylindrical. As I have explained earlier, the R dot mesh lines are similar to the familiar X dot mesh, Y dot mesh, and the Z dot mesh, except that the R dot mesh locations and spacing are radial relative to the Z axis in micron. This show the radial values. R dot mesh location from 0 to 17 nanometer, the spacing is 9 nanometer. Next, R dot mesh location up to the 20 nanometer, the spacing is 0.0009. It will be continue up to the 32 nanometer with the spacing 0.009. Next, we have to specify the angular meshing. A dot mesh location from 0 to 360 degree, the spacing is 20. The important thing to note down that the location and the spacing on the angular mesh line specify location and spacing in degrees of rotation about the axis. The z dot mesh lines are exactly the same as we have already discussed in the last slide. It looks like a x dot meshing location and spacing. Please note down this code. We have specified the z dot meshing from minus 20 nanometer to the positive 20 nanometer. This means length of the device is approximate 40 nanometer. Next, we have to define the region. To define the structure in the 3D or cylindrical coordinate, you must specify Z dot minimum, Z dot maximum, A dot minimum, A dot maximum, R dot minimum, and R dot maximum in region, electrode, and doping statement. Reason number 1 for material silicon and the positional parameter for the Z direction, angular direction, and the radial direction is mentioned in the code. The second material is again silicon. The positional parameter is specified in the presentation. For the third reason, the material parameter is HFO2 and their positional parameter are specified in the code. Next, the reason parameter is polysilicon. The parameters are mentioned in the code. The next parameter is next reason is again silicon. Next, you have to define the electrode statement. Again, you can note that we have mentioned the Z parameter and the R parameter in the electrode statement, in the drain, gate, and source electrode statement. Next is the doping statement. We have specified the Z dot minimum, Z dot maximum, R dot minimum, R dot maximum in the doping statement also, in which I have taken the source and the drain doping are same and the channel doping is different. The source and drain doping is 10 raised to power 20 and the channel doping is 10 raised to power 60. Next, we have to define the contact, gate, source, and drain. The work function of the gate metal is 4.9. Please note down. Next, I have defined in the code the model statement. The first one is SRS model. Second model is BQP.QDR. I have already mentioned that we have to use 4 for the cylindrical structure. BQP.N, the value of the gamma parameter is 1.2 and the alpha parameter is 0.5. Next, we have to define the method statement, in which we are using the method Newton and the block, and we have specified the various IT limits and block IT limit, trap maximum. The value of the maximum type I have taken 6 and the VACTMD.INC for the negative differential mobility is 0.01 for the carrier 2. We are using the statement solve initial and the solve previous. If you want to understand about these solve statement, please go to my previous video. I have already explained in my previous video about these solve statement. One more thing to note down, that the change in the drain voltage must be gradually, not sharply. If you are changing the voltage from the V drain to direct from 0.2 and 0.8 volt, then the convergence problem takes place. Next, I have saved the structure file with the name CY1. Next is the solve statement for the AC simulation. For capacitance and the conductance, we get 0 to 1 volt with the step voltage 0.05. Next, I have saved the structure file in CY1, and for display, we are using the Tonyplot 3D command to observe the 3D cylindrical file. Next, we are using the Tonyplot CY1 for the display the log file in the Tonyplot. Next is the quit. After run this code, you will get the structure file just like that, and the log file this one. The maximum value of the on current is more than 10 raised to power minus 4 because we are using the HFO2 as the oxide material, and the off current is also quite low, is approximate 10 raised to power minus 13. For obtaining the data from the log file, you have to simply go to the file, then the export, will save in common separated value format, or we can say that in Excel format. You can save anywhere. I am saving this data in D in Silvaco code with the name export with the extension CSV. Okay, file already exit with the name. Do you want to overwrite? I don't have any problem. Yes. Export. Next one. If you want to extract data from the structure file, then what will you do? Go to the tool, cut plane option. You have to set this pan angle is to at 270. It is already mentioned as 270. Each angle is 90. If the elevation is there, you have to set at 0. You can set by moving this, and you can set the elevation directly at 0. If you are using the latest version of the Silvaco, you have to click on swept X5, then slice. After that, OK. You will get the structure file in 2D format. If you want to extract data from the structure file, you have to select the 2D file, then tool, then cut line. You will choose the cut line horizontally and make a cut line from SI-SiO2 interface 1 nanometer away from the SI-SiO2 interface. You will get the topping. If you want to check the different value, you can check the factor concentration, composition, conduction band density, valence band density, electron concentration, hole concentration, electric field in extraction, electric field in Y traction, electric field in Z traction, total electric field, electron concentration, hole concentration. You can get all the value, valence band density, potential, everything you will get from here. Okay, what will you have to do after making the cut line? You have to choose this in. You have to choose this file, this format, and save as in that format. I saved in that format as Girish. My computer, I will save in D, nanowire, save. Next, we have to call this that file, open D nanowire, the that file, Girish one, open it. This is the that file. Now you can extract the data in CSV format from this dat file. Select it, file, save as. You can save. Now it is directly in CSV or Excel format. Select CSV, Girish, Girish 12, and saved in same place D nanowire. Save it. Now go to the nanowire Girish 12. This is the Excel file. Open it. You will get all the values with respect to horizontal axis of the channel. You will get the absolute doping, electron and hole concentration, potential, electric field in X and Y direction. Everything you will get in one Excel file. get all the data in a Excel format, log file as well as vector file. It is all for today. If you have any query, you can contact me at my